So just want to introduce myself. So my name is Torsten Strauss. I'm a Microsoft Most Valuable Professional for a while, living in Germany and focusing on very large SQL Server environments. Yeah, I'm responsible to make them fast. So which is even more important in times of Azure, where, you can save a lot of costs when SQL Server is performing well. And that is a reason why I think it is even more important to understand the SQL Server engine. And one topic I would like to present is InMemory OLTP. And I would like to discuss especially the design principles. So what is the reason that Microsoft decided to introduce InMemory OLTP? I think it was released in SQL Server 2014, if I remember correctly, but honestly, at that point in time, it was not really, I would say, really functional. I mean, InMemory OLTP was there, but a lot of restrictions, a lot of limitations, and sometimes it was impossible to migrate to an InMemory OLTP database because of all these limitations. So in SQL Server 2019, we still have some limitations, but honestly, it is, again, it really depends on your environment, on your database. You have to check whether migration can work. And I think before you check whether, I would say, these features, T-SQL, syntax, and everything like this is supported in 2019 InMemory OLTP, it is worth to understand whether there is a need and whether it is useful to migrate, because I presented this session already several times, and the feedback from the audience is that they always think that InMemory OLTP is much faster, and they have to neglect maintenance and all this kind of stuff. To make it short, this is not true. So InMemory OLTP is not always faster than the traditional on-disk storage engine. And you have to maintain the database as well as you know already from the on-disk database. So we have different issues. We have different performance issues we need to solve even with InMemory OLTP. And again, the reason why Microsoft decided to introduce InMemory OLTP is mainly about avoid physical reads. So you know that a physical read is something which is the most expensive operation the SQL Server engine has to do. So, but we also know that once the data is written from the traditional on-disk storage engine into the buffer pool, there is no physical read anymore. It is just a logical read. There is no logical read without a physical read for sure. But once the data are in the data buffer pool, I mean, it is some kind of in-memory OLTP. Yeah, so that is not the reason, I would say. Nevertheless, that was one of the reasons that Microsoft decided to introduce in-memory OLTP, where it is the other way around. The interaction with the operational, with the disk, I would say, is really reduced. We still have some information which will send to the transaction log, depending on the durability of in-memory tables. But even so, the number of records and the size of the transaction record is also reduced. You know? So that's maybe a reason to migrate, but honestly, in these days, an SSD drive or Fusion IO card is horrible fast. You know, that is, I think, not really a reason to change and to think about InMemory OLTP. So something which really matters is that InMemory OLTP completely eliminates latches and also locks. That means we have a so-called multi-version concurrency control, which makes locking and latching completely, I would say, there is nothing like a mechanism in place. Yeah? So latches, and we will talk about latches, we will talk about locks, they do not exist in InMemory OLTP. And I think that is definitely something you need to consider, right? So, and maybe you can argue that okay, this is something which I can achieve with read-committed snapshot isolation, with the version store in TIMTB. That's true, but a lot of I/O is required for these kind of, I would say, row versioning in TIMTB, which is really, really heavy, especially when you have to update or delete records. And writers still block writers. So in InMemory OLTP, writers do not even block writers. So there are no locks. And this is something which we will see later on. So I would say you all know, hopefully, that whenever SQL Server has to execute a T-SQL command, which can be a stored procedure, which can be an ad hoc query or whatever, SQL Server have to prepare a so-called execution plan before really executing the query. So that is some kind of an expensive operation. So we will talk about, optimization. We have optimization phase 1 up to 2, up to 3. So there are a lot of CPU cycles, a lot of memory is consumed because all these alternatives will be saved in the so-called memo structure, which consumes memory. So it's really a horrible, complex, and sometimes really CPU intensive operation. So, and in InMemory OLTP, we do not have something like an optimization. So the overall code is directly written in C code, which introduces SQL Server storage engine to do some operations, and there is no interpretation anymore. There is no interpretation needed, and there's also no compilation or even recompilation. That is sometimes bad, as we will see later on. Sometimes it is good because if you see that you have a lot of recompiles because of statistic changed, or there are several reasons why you run in a recompile, yeah, then maybe it is another reason to think about InMemory OLTP. The last point, and again, these kind of arguments I took them from the official Microsoft on the documentation. The last argument is avoid non-optimal plans. So whenever SQL Server creates an execution plan, the overall, or the structure and the operators which are used in the execution plan assumes that all data are on disk only. So because this is for sure the worst case. So it still can be true that some of the data pages are not in the buffer pool. So SQL Server have to load them by physical I/O into the buffer pool first, which is again a much, or I would say, very expensive operation. And the costs, so-called estimated subtree cost of an execution plan, is based on the assumption that the data reside on disk and not in the buffer pool, which is in these days not, I would say, not always the truth. Maybe even it is more likely that we have data in memory rather than on disk. Yeah? So, but again, so because of this algorithm or this kind of rule, yeah, the plans the SQL Server optimizer creates are not the optimal plan. Okay. Let me introduce, or let me prove the first argument, which is avoid physical reads. So I'm using the AdventureBox 2017 database, so nothing special. And I create a record with 5 million rows. And before I'm doing it, so let me just say, 1 second. I just want to switch to high performance. Okay, cool. So here you can see this is just a table I'm going to create, which is a copy of another table which I created before, which is nothing else than the Cartesian product of sales order detail. And this time I'm inserting 5 million rows into a new table, so we have a heap. So next command is creating a clustered index on the table I created, just to make sure that we have a comparable, I would say, execution or sample, because in-memory OLTP always requires to have at least one index. Because we will see later on that in the memory OLTP, we do not have pages. We do not have an IRM pages. IRM page, which is nothing else than the bracket, yeah, which tells the SQL Server storage engine which kind of pages belongs to a specific table. Okay. So instead, we always have an index which links all the records. So this is something like we call it the glue. So, and we do not have pages. Instead, we have records. So it's a complete different structure. Yeah? So I flush the buffer cache by checkpoint, drop clean buffers, enable statistics. The first statement I'm going to execute is just count all records from the table I created. So it's very likely that we will see something like 5 million rows, hopefully. Let me execute this one. 5 million rows. So we have an execution plan here. We can see because of the costs of the execution plan, which is sometimes it is 32, sometimes it is 25. So it really depends. I do not know why it is not that deterministic, but okay, this time is 25. But I will use my these figures because then I can already get the figures from my comments rather than going to the message and all this kind of additional stuff. So it will shorten the presentation a bit. So assume that we have a cost of 32. So we have a clustered index scan. So and here we can see all the rows. SQL Server have to read all the rows, and we spent 32,000 logical reads. And the CPU time and the elapsed time is close to 1.5 seconds. Okay. So in order to achieve in order to achieve the statement and just count all rows within table, SQL Server will read all the pages from disk and send them to the buffer pool. And we have one view. This view is called this DMO is buffer descriptors, which tells us which pages are currently loaded into the buffer cache. So we can see the database name, we can see the schema, we can see the object name, which is sales order detail medium. So that is a table which we currently used. So, and we have a lot of pages here. So every record is one page, right? So, and one page is 8 kilobyte big. Means if I now aggregate all the data from the buffer cache, just counting the row and multiply with 8 kilobyte, then we will end up with something like 250 megabytes for the data page. And then we have, because we have a clustered table, so we have a clustered index. We have an index page, which is root, and maybe we have an intermediate level. I do not know how many levels we have, but that really doesn't matter. In the end, we will end up with 250 megabytes. Perfect. So I will create a database which supports in-memory OLTP. Do this. In order to create a database which supports in-memory OLTP, we just have to add a file group which is optimized for memory objects. So that is why you can see file group. You can name it memory optimized, contains memory optimized data. Then you have to give a few properties and your database is created. So that is not a big deal. I set the recovery model to simple, just to make it comparable to the AdventureBox 2017 database, which is also currently operating in a simple recovery model. So it takes a moment. Okay. I wonder why it takes that long. Okay, but SQL Server was able to create the database perfectly fine. Now I use the database, and in order to exchange data between a traditional database and an in-memory OLTP database, or even between two in-memory OLTP databases, you have to use the temp database in between. So there is no direct link. So there is no cross-database query when you use in-memory OLTP database. let me create the structure of the in-memory OLTP table. You can see it's very easy. We just need to add an index. And this time I add a so-called, what is it, a hash index. So we have to name the number of buckets. In this case, I have 5 million buckets. I do not want to talk about buckets, but let's say this is a comparable index, or this is an index which you can compare to the clustered index which I created before. So the structure is there. And now I'm just exchanging data between AdventureBox 2017 and the temp DB. From the temp DB, I populate the in-memory OLTP table. Let me resize it a little bit. Okay, it is there. So now I have 5 million rows in the formerly created in-memory OLTP table. So this was just about preparation. So very easy, but now I'm counting the same number of records. I count from sales order detail medium, which is the in-memory OLTP table. So we have an execution plan, but this time we can see that the costs are down. Here again, it is not really deterministic, but what you can see is that we do not have any kind of estimated I/O cost. So it's in the middle. I cannot move the mouse because otherwise the pop-up window will disappear. But in the middle, you can see estimated I/O cost. And the overall plan is much cheaper than the other plan. This time we had, I think, 22 or 25. And for the same query in an in-memory OLTP database, we have an estimated subquery cost of 6.4. So, but now think about, we have an estimated subquery cost, an estimated I/O cost of 0. When I execute the same query in the on-disk database, which is the AdventureBox 2017 database, there is no I/O anymore. We do not have any physical I/O anymore because all the data are in buffer pool. That is the reason why we were able to see all the data in our buffer pool. We know already that it consumes 250 megabytes. And that is why the estimated subtree costs are not precise. There's always the assumption that SQL Server have to read the data from the MDF file, which is not true. That is why the estimated subtree costs are never, ever precise. This time, SQL Server can assume, and there's a guarantee, that SQL Server do not have to read the data from disk because we use an in-memory OLTP database instead. And that is why the overall estimated subtree costs are much cheaper, because this is just the difference between the former plan and the estimated I/O cost, which is 0 now, and before it was something about, I don't know, 19, I guess. You know? This is the difference, nothing else. So, but you can see that the CPU time is also reduced. I would say to the half. So we can see 719 milliseconds, and the elapsed time is down to 740 milliseconds, which is the half. So when we now ask SQL Server about the memory footprint in our data pool, buffer, we do not see anything. So now you wonder, that's perfect. So we have a much faster query. We have all the data in memory, but I do not have any kind of memory footprint. For sure, this is not true. We have to use another DMV, which is called DMDB-XTP. XTP is for Hackathon, which is the project name of in-memory OLTP. And you can see memory consumers is comparable to the DMOS buffer descriptors. So when I ask about the size of the table, we can see something interesting. We have the allocated bytes and the used bytes, and we have the hash and the varchar. So we have the data and we have the index, which is some kind of comparable to the index pages and the data pages. So when I execute the, or I can do the math on the screen. So you can see the hash index allocates 64 megabytes, and the heap allocates almost 400 megabytes. That is much, much more than the comparable on-disk table, which only consumes 250 megabytes. So we will end up with an additional, I would say, 150 megabytes. Or even more, sorry, I need to add the buckets for the index as well. So we have 250 megabytes comparing to 460 megabytes. Meaning this is a complete different memory footprint. That is something you need to learn. All your table or the memory impact will be much higher when you use InMemory OLTP. So let me go down. Now I want to reduce, I want to try to reduce the CPU time and the elapsed time, yeah, just trying to make the query even faster. So there's, or the other way around, there is something which is named query interopt engine. So the query interopt engine makes it possible to query data which currently are located in the memory OLTP table with traditional interpreted T-SQL commands. That is, we did it. So select count from in-memory OLTP table. That's possible. But in order to benefit from the in-memory OLTP feature, I would call it feature, or architecture, maybe that's better, we can create a so-called natively compiled stored procedure, which is again just C code. So that is how it works. Create procedure test with schema binding, which is mandatory. Native compilation, it's also mandatory. Then we have to say begin atomic with. Then we have 3 different kind of transaction levels. The language is, I think, not mandatory. I'm not quite sure. And here we can see the T-SQL command. Select count from in-memory OLTP table. Let me do this. This time I'm not executing an ad hoc statement. Instead, I'm executing the natively compiled stored procedure. So let me do this. And it takes longer because I still, or the other way around, I still visualize the execution plan. So let me do it a second time. So we can see that the CPU time is down to 300 milliseconds, which is 1/5 of the original query. And the elapsed time, for sure, the user experience is also down to 300 milliseconds. That is a benefit of using interpreted, natively compiled stored procedure instead of interpreted T-SQL commands. So when you want to use in-memory OLTP and really want to benefit from the performance of in-memory OLTP, there is no way not to use natively compiled stored procedure. That really gives you a performance benefit, but not in all cases. You know? Do some housekeeping here, and let's talk about ledges and blocks. So what is a ledge? A ledge is used to protect the internal structure. So what is an internal structure? So mainly, I would say this is a page. So we have other internal structures, but to keep it very simple, it is a page. So, and because it is a page, it is applied on a physical level. So we talk about page ledges, we talk about page I/O ledges, and so forth. It is very cheap to manage and maintain. The duration is really short. It is not transaction based, so you cannot say, I don't know, you want to run the statement with read uncommitted. Yeah, so that means you accept dirty pages, but this has no impact on ledges. Ledges is something the internal storage engine have to protect the page. We will see this because it has to avoid that, or it has to avoid that several threads will update the same page at the same time, because then we will end up with a so-called lost update issue. One thread will read the page, and the page consists of 3 sections. So we have the page header, which is 96 byte big. Then we have the so-called payload, which is something about 80-60 bytes. And then we have the row offset array, which is at least 36 bytes big. So in the page header itself, there's one information which tells SQL Server, and to be precise, the thread, where to insert the next record. So what is the position? What is so-called offset? And the first offset, when the table is empty, is 96. It's a 90 or a 97th byte. So SQL Server will insert the record there. When another thread will read the information from the page header where to insert the next record, at the same time, it will also get the information, insert the record on the 97th byte. And the thread will insert the record at the same position. So therefore, we will end up with a lost update issue. So the last thread will overwrite the first record, which was inserted by the first thread. And that is why SQL Server have to latch a page. This is a page latch, right? Called page load. It's a very common and very prominent wait type. Yeah. So also, I would say not that easy to avoid. One possibility to avoid latches is to use InMemory OLTP. Because again, in InMemory OLTP, we do not have pages. We have records. We have multi-version concurrency control, as we will see, which completely eliminates the need of latches. So this is something you must understand. So what is a lock? Just as a comparison, because I already told you InMemory OLTP is a lock and latch free. So a lock is applied on a logical level. It is just there because we have something like the ACID rule in place. So ACID, yeah, atomic, consistency, isolated, durable. So we will talk about consistency and isolated, especially isolated when we talk about locks. When we do not rely on the ACID rule, and I mean, there's one transaction isolation level which is very close to this, which is the no lock or read uncommitted transaction isolation level. Then there is no need for any kind of lock. But in RDBMS system, always have to ensure the ACID rule. And that is the reason why we have a so-called lock manager in place. That means for every lock, which is dependent, and we are just talking about the exclusive lock, the duration of the exclusive lock is dependent on the transaction isolation level. Sorry, not the exclusive. It is a shared lock. Sorry, the shared lock is dependent on the transaction isolation level. The exclusive lock is something which you cannot avoid and which you cannot influence in any way. So you can see that the lock is for sure manage the transaction concurrency, as already mentioned, and it guarantees that the transactions are isolated and consistent. So again, this is the ACID rule. So we have several types of latches. So we can see, for example, we have a shared latch, we have an update latch, and an exclusive latch. Shared latch is there whenever the SQL Server has to read a page. An update means SQL Server have to update a page. An exclusive lock or a latch is whenever a page has to be modified, which is by inserting or deleting the records. So there's a matrix, as you can see, which is very close to the matrix you know already from the locking and locking mechanism. So shared latch is compatible with another shared latch, with an update latch, but not with an exclusive latch. And an exclusive latch is not compatible with any other latch type. So, and that is the reason why whenever several threads are trying to insert records into the same page at the same time, which is, by the way, possible from a blocking perspective, because we do not run in a block, because only the resource, which is the new inserted record, is locked. But from a latch perspective, that is not possible. Again, because SQL Server have to update the position where to insert the next record. So let me go down. And first of all, there's one let's say, really famous DMV. It is a DM OS wait stats. So whenever you do performance tuning, that should be the first DMV you should analyze. So, and we can see, for example, that since SQL Server was restarted, which is maybe, I don't know, 40 minutes ago, SQL Server was waiting 8,330 milliseconds just on the exclusive ledge. Then we have the page ledges. You can see we have a few more page ledges. And then we have page IO ledges. That is whenever SQL Server have to read pages from disk in order to write or in order to read them. So let me reset the wait statistics here. And let's talk about page ledges. So I will create a table in the AdventureBox 2017 database. So a traditional on disk storage table. How it works, just a table with an integer, ever increasing key, primary key on top of it, and we have a column 2, which is a character 100, which is a default of A, just to have some kind of a filler. I will reset the wait stats another time, and I will run OStress. So OStress is a tool which comes for free. Second. Okay, CMD. I guess I need to run it as an administrator. At least that is always a good idea. And OStress can simulate a workload. So you can see how it works. You need to connect to your server. And I will execute a specific statement. And I will open the statement for you. But the statement is executed 100 times on 300 parallel threads. So, and the file which I'm now going to execute is nothing else than this command: insert into the table, right, with all default values. It means column 2 will be always A, and column 1 will increase by 1 by every new record. And I will insert, I will reset the wait stats another time because I was talking quite long. So I'm executing the query, and while it is executing, I will get some information from waiting task. We can see that we are running in a page ledge contention. That is, we have several sessions. Let's consider that one session is one thread. And we have the reason why the thread is waiting. It is waiting for page ledge exclusive. And I'm pretty sure when I execute the same query another time, I will also see a page ledge shared. Because again, so SQL Server have to read the information where to insert the record into the page. That is a shared ledge. And once the record is inserted, it has to update the position, the offset, where to insert the next record. That is an exclusive ledge. Let me dump the page. Just one sample here. Issue here. I need to replace it with a comma. Here we go. So you can see that the M type 1 is actually the data page. So M type 1 is the data page. That means SQL Server has to insert all records on the very last, or on the rightmost page within the balance tree, right? Because we have an ever-increasing key, and it is a primary key. So therefore, SQL Server have to insert the records in a sorted order. Because we have an ever-increasing key, we have a contention on the rightmost page of the balance tree, which is the data page. There's another information. I mentioned this already several times, but we can see the position where to insert the next record here. It is called M3 count, which tells you where to insert the next record. Okay, so that is why we have a page ledge contention. So the execution is done. See it here, it took 12 seconds. And now I'm asking SQL Server at the time the engine was waiting for the page ledge, which is either the exclusive or the shared ledge. We can see that we wait, or SQL Server waits almost 370,000 milliseconds just on the page ledge. And that is per thread, right? You remember that we are running the threads in parallel. So let me do the same with an InMemory OLTP database, and I will reset the InMemory OLTP database just to make sure that we do not have any leftover. I set the recovery model to simple once it's done. I use the memory optimized table database. I create a table, the memory OLTP table. You can see it here, durability, schema, and data. So we have column 1, primary key, which is ever increasing, another column 2, and I will get statistics and run the same statement another time, but this time on the InMemory OLTP database. So this time I cannot see any wait stats which are caused by inserting the records into the InMemory OLTP table. It was a little bit faster, but this is, I guess, neglectable. But nevertheless, you can see I do not have to raise any page ledges here. That's completely different. I will tell you how the internal structure of a table, of an InMemory OLTP table, looks like. So let me open InMemory OLTP and say, where is it? 2# index. That is how an InMemory OLTP table looks like. As mentioned, we need to have at least one index. This time we have a hash index. This is the index where we need to set the right number of buckets. This is what I already did. We can see on the left-hand side we have a hash index. I would say it is something like we have hash buckets, and within the hash bucket we have the InMemory OLTP address to the record. It means when I'm searching for I think it is Adam, let's say the first name, when I search for all records within the InMemory OLTP table, which begins with an A, SQL Server have to look into the hash index map on the left-hand side. And because of the so-called hash function, which is deterministic, SQL Server knows in which bucket to look for the A. So that it is in this case, but there's no guarantee the first bucket. But let's assume it is the first bucket. In the first bucket, we do not have any information about the index, just the link, the InMemory OLTP address to the first record, which is Adam. And now there's another link, another index. That is the reason why we have to have always at least one index. That is a glue between the records. It is a link to the next record. You can see N, which she lives in Cincinnati. Another record, N in New York. And that's it. That means SQL Server always have to read the entire chain of the index link, which is related to the index, which is related to the hash function A. So, and the reason why we do not have to, or SQL Server do not have to care about ledges, do not have to care about logs, is that we have a multi-version concurrency control implemented. You can see it here. So N lived in New York. So between timestamp, transaction timestamp 5 and 100. And at the point of 100, N was updated, so the record was updated. She moved to Cincinnati. So that means the validity of this record, or this record, is a current valid record. So that is the current record. That is a former record. So, and depending on the timestamp, another transaction, which is maybe still running, now knows which record it has to read. So when the transaction was raised between the transaction timestamp 5 and 100, the other transaction will still read N in New York. When a new transaction is raised and the transaction begin timestamp is older than 100, it will skip this record and instead it will read N in Cincinnati. That is the reason why a record, or the multi-version concurrency control, is the reason why SQL Server and the engine never ever have to update a record apart from the begin timestamp and the end timestamp. But the payload, so N Cincinnati, N New York, will be never ever updated anymore. And because of this, we have several versions of the same record for a specific point in time. There is no need for a lock, there is no need for a block, and there is no need for a ledge. We do not even have pages, we just have records. So that is how it works. So let me go back to Management Studio. We do some housekeeping. I will introduce locks. So you know that SQL Server by default is running in read committed in the read committed transaction isolation level, which means it is running in a pessimistic concurrency. Pessimistic concurrency relies on locks and blocks, whereas optimistic concurrency, that is snapshot isolation or read committed snapshot isolation, is not based on blocks anymore. Instead, it is based on the version store, which resides in the tempdb, which is some kind of, I would say, some kind of comparable of the multi-version concurrency control we have seen in the InMemory OLTP table. So the pessimistic concurrency is, or the other way around. In the pessimistic concurrency, readers will block writers, writers will block readers, writers will block writers, but readers do not block readers. The difference is, so in an optimistic concurrency control, readers do not block writers and writers do not block readers, but writers will still block writers, right? So let me present how it works in a traditional database. So we use AdventureBox 2017, which is not our InMemory OLTP database. I will clear the wait stats and we'll raise the transaction. So you can see this is an explicit transaction, and I set the transaction level to repeatable read in order to make sure that even for the read of person-person, the entire, I would say, range of person-person is locked until I either raise a commit or roll back. So I have an open transaction, so which I can see here. This is mainly tran logs with a few more information. We can see that the current session is 84, and 84 have several logs on person-person, metadata. So a lot of, I would say, or a few other objects are involved here, but mainly we can see that there's one shared log on the first record, which is, let me go down, let me go up, which was business entity ID equal to 1. So we have a log on one record on this table. So let me run this in another session. So here I'm trying to update the record which I'm currently reading in the other session. This is not possible. I have to wait, and I have to wait until I decide to roll back or to commit the transaction, which is currently open in this session. So when we have a closer look on at the logs, we can see that 84 will have the log, the shared log to be precise, on the first record in person. And we have another session, 91, which is currently running, which is waiting for an exclusive log to update the record. That is not possible. Because, again, an exclusive log is never, ever compatible with any other logging type. So let me close this one. For sure, now the other transaction was executed. I will roll back both of them so that we have the same table as before. And now I will do the same within the in-memory optimized database. Data table, person, and just insert records from the temporal table, from the tempdb, that we do not can access another database from the memory OLTP database. That is the reason why we always have to use the tempdb in between. And I will do the same stuff another time. I have an open transaction, select person, and in memory OLTP, as mentioned, we have 3 different kind of transaction isolation level. I decided for a snapshot. And what we can see is, so the transaction is still open. When I run the same statement another time, which tells me about the logs, we do not have any log apart from the schema stability log on the table itself, to ensure that no other transaction at the same time can drop the table. But we do not have any logs on any resource apart from the table itself. So that means when I now insert or update the same record I was trying to update in the AdventureBox 2017 database, and now do the same stuff in the memory optimized database, it is possible. Of course, when I ask d and tran logs another time, we still see that I do not have any log. Because I do not have a log, I cannot run in a blocking situation. And what happens is, you remember this picture, we just created another version of the previous record, which becomes the actual record for all new transactions. Because the begin transactions, or the end transaction state, the end transaction timestamp of the formerly updated record is now changed. So this is not the current record anymore, but instead we inserted a new record, which means an update is never ever an update. An update is an insert, and an update just on the end, or the end transaction timestamp to invalid the record. Right? So we can see that there is no current wait type, which is LCK for log, M for and X for exclusive. Very surprising. Do some housekeeping. Okay, and honestly, I'm a little bit running out of time. Just want to spend another minute on the C code. So you remember that I already introduced natively compiled sort procedure to you. So whenever you create a sort procedure and do not even execute a natively compiled sort procedure, the code is already written. That means we have a DLL, which is just there for debugging purposes. Every other information, so the C code, is just saved in memory. That means another time we do not have any need for a physical I/O. The problem is, because you do not execute the stored procedure or the other way around. SQL Server compiles the stored procedure even before executing the natively compiled stored procedure. The plan always assumes that you have optimized for unknown, because SQL Server cannot foresee the parameters you're passing to the natively stored procedure. So that is the reason why the internal C code is always optimized for an unknown parameter set, which can be sometimes an issue, because even if you add more and more indexes to the table in order to support the stored procedure, SQL Server will never ever recompile the C code, which means the indexes are completely useless. In order to benefit from the new indexes, you have to recompile the stored procedure manually, and then you get a new C code. I guess that's it. Do you have any questions about InMemory OLTP?
If you have a question, you can type it in the chat, or you can come off of mute and ask Torsten yourself. I think it was a great presentation, a lot of good technical information. I think people are just trying to absorb it.
Thanks a lot.
Sure. I don't see a lot of questions though, but still a great presentation. Well, I'm going to kind of close the meeting out, guys. I'll have this recording up probably in a couple hours. Oh yeah, there's just a couple of comments. No question. I just realized how much more I have to learn. Yeah, guys, the SQL stack, there are a lot of engine related things like Torsten's talking about, operational things that you have to learn. So Brendan and Brad, thanking you very much for the presentation. And I concur with that. Thank you very much. Very informative.
Thanks a lot. Thanks a lot.
I'll stop recording, and I'll have this recording